All right, welcome back. So let's continue where we left off from last time, where I gave you the 3 practice problems of a game of die. And it is appropriately named because this is often the bane of a beginner organic chemistry student, because these problems tend to get really confusing. But we will go through this together and hopefully help you clarify some of the questions or confusion that you had about these problems. So the first pair of molecules that I gave you was this pair right here. And to determine whether they are diastereomers, identical, or enantiomers, it is often helpful to redraw these molecules. So first, what I will do is that I'm going to rotate this bond so that the molecule now looks like this. So that a molecule looks like this. And so how did I do this? Well, essentially I rotated 180 degrees so that this CH bond in purple right here became this CH3 bond in, or this CC bond in purple right there. And so because this hydroxyl group here was originally pointing into the page, if we rotate it 180 degrees, it's going to be pointing out of the page. Okay? And now let's do the same for the other molecule. So if we do this for the other molecule, we will get, if we rotate right here 180 degrees, we will get, we'll get this molecule right here. So now it might be easier for you to tell if these molecules are enantiomers, diastereomers, or identical. And in particular, you might notice that there is a plane right here. And if you reflect or rotate the molecule across that plane, if you, for example, just think about flipping the molecule 180 degrees around that axis of rotation, you will get this. And now you can clearly see that these two molecules are identical. So yeah, in a lot of these problems, it is often helpful to redraw molecules so that you can clearly see if there are any planes of symmetry that might allow them to be identical. Because if you didn't do that, you might conclude that, if you assign configurations, then the configuration would be 1, 2, 3. You would say this is our configuration. If you assign a good configuration here, I believe if you do 1, 2, 3 here, you would end up with some configuration, but essentially the point is if you did configurations, you might have accidentally thought that these two were enantiomers, whereas in reality, they are actually identical. Right, so let's lastly do the other two problems from last time. So the second problem that I gave you guys was this pair. So I gave you where both of the, so similar to the first problem, except now I've changed up that instead of alternating dashes, they would alternate, or they would either both be dashes or both be wedges. So here you would have OH as a dash and OH as a dash. And here, from just similar to before, we can do the same thing. where we can try to arrange this so that it looks, so that we can look at these molecules in a way where it's easy to tell if there's a plane of symmetry. Okay, so if we rotate again 180 degrees around this bond, then we will get, so you'll still have this OH as a wedge, but now this will be, or actually, this will again be CH3 down here, and this will be a wedge. And if we do the same thing for this bottom molecule, we will see that this will become a wedge, and then this is a dash. And so now if you compare these molecules, you can hopefully see that they are mirror images of each other. Because if you try to rotate this molecule around, like for example, this plane right here, you would just get the same molecule back. So if you try to rotate, unlike last time when we rotated, we saw that they became the same molecule. This time, when we rotate, we will still get this molecule. And try to see if you can visualize this in your head. If, let's say, this OH group was originally pointing out of the page, if you rotate 100 degrees or 180 degrees around this axis, it'll just go into the page now and become a dash. And clearly, hopefully you will be able to convince yourself that these two molecules are indeed mirror images of each other and thus are enantiomers. All right, and lastly, the third problem that I gave you guys was also similar in that you had to look for mirror planes to identify if the molecules were identical or not. So the third problem, I believe, was where I gave you this pair of molecules. And what you might recognize after having seen our first two examples is that there is a plane of symmetry along this axis. So bear with my drawings, but essentially if you rotate this molecule, so this left molecule right here at 180 degrees, you will see that this hydroxyl group will become this hydroxyl group, because if it's pointing out of the page, it will now point into the page after rotating 180 degrees. And these two groups will become these two groups. So like in other words, these molecules are also identical. Okay, so now that we have some intuition for how sometimes, even though there might be chiral centers in our molecules, sometimes there might be symmetry that causes them to actually not be enantiomers, that brings us to the idea of meso compounds. And so that's exactly what we just saw. Here, instead of having a CH3 group right here, we're having a carboxylic acid group. But essentially, it's the same concept that we just saw. When we rotate around this bond right here by 180 degrees, we will see that this and these two molecules will not be identical. Whereas if you rotate for this meso compound right here, you will see that even if you draw what seems to be the enantiomer, so you might think that this molecule is the enantiomer, but if you were to rotate both of these 180 degrees, so again, we're rotating the bond 180 degrees, you'll see that they become the same molecule because they have a plane of symmetry. So last topic I want to cover in this stereochemistry lecture are Fission projections, because you'll see these commonly, especially for a lot of biochemistry molecules. So essentially, Fission projection is another way of drawing molecules in 3D. And the way these Fission projections are drawn is that the horizontal bonds, so these bonds in blue, are implied to be wedges, so pointing out of the page. And these vertical bonds are implied to be dashes. And these also apply to these bonds as well. But for the sake of clarity, we will only show that these two topmost and bottommost bonds are going into the page. A good mnemonic for remembering this is SUP. And you can probably tell, or maybe this is the wrong color to use for this, but you can probably tell why we use SUP for remembering this. Because if you're on the side, then you're up. So side, up, SUP. Okay, let's move on. So yeah, let's go to an example of actually how you would actually convert this drawing to a normal bond line structure. And for this molecule, it might be a little bit harder since it's a longer molecule, but let's just go through this as an example so that if you see smaller molecules, it'll be easier. So one thing we can do is we can start from this atom right here. And so if we start from that, we might say, and let's say that we are looking, so the way we look at this atom, say we're looking down. So if we look downwards on this atom, we will see that maybe this first carbon starts here. And so then, because this CH3 group is a dash going into the page, we will see that this CH3 will be going down. And so similarly for these other inner carbons, 2, 3. So if this is carbon 1, if we look at carbon 2, then we also know that it must be, the two vertical edges must also be going down. So therefore carbon 2 should be above carbon 1 and 3. And lastly, this uppermost CH3 group will also be pointing downwards. Okay, and so now the hard part's actually done. So the hard part is trying to figure out which view you're going to look at this molecule. And if you look from that view, how would essentially the backbone of this molecule look like? And so now filling the side groups is going to be easier. So if we look at carbon 1, we see that it has a hydroxyl group attached and also this CH2, CH3 ethyl group. And so we're going to define, doesn't matter how you define this, but we're going to define this direction as going to be a wedge in our bond line structure, our regular structure, not Fission projection, and this direction as going to be a dash. And so therefore, this OH group, it's going to be pointing up, but it's going to be a dash right here. And similarly, this is also going to be pointing up, but this CH2, CH3 group, I'll call it ET for ethyl, is going to be a wedge also pointing up. And so I'm just going to erase this just to prevent clutter and maybe write it down here instead. So we do the same thing for carbon 2. We point upwards with a dash, and we point outwards or upwards with a wedge for the bromine. And lastly, for CH3, we're going to do the same thing. We're going to do dash and then wedge. And so hopefully you can convince yourself that if you look at this molecule from this vertical view, what you're going to see is this Fission projection. So I'll leave you to think about that on your own. But lastly, in our last minute or two, we are going to basically talk about why Fission projections are useful. So Fission projections are mainly useful for quickly identifying meso compounds. So back in our last few examples, to identify a plane of symmetry, we had to sort of rotate our molecule in our mind and try to draw them out, and it took a little bit of a while. But here with Fission projections, it's really easy to see if a compound has a plane of symmetry. I'll give you a moment to think about which of these compounds is a meso compound with a plane of symmetry. But you might already be thinking that it's number 3 right here, because you can clearly see there's a line of symmetry right here, whereas the other 2 compounds do not have a line of symmetry. So as a result, Fission projections are really powerful for quickly allowing people to determine whether there is a plane of symmetry in a molecule. And with that, hopefully you guys feel a little bit better about determining stereochemistry in different molecules. All right, so that ends the video series for stereochemistry. In the next video, I'll be talking more about acids and bases. Thank you.